the white token. Right, so we can just it's easier for us to. And this is why it's called a hazard, because again it's considered as this this contest. So the state of 1 is not a good state, right? So when patient dies, so that's why it's called a hazard. It's the likelihood for that patient to die at any point of time. Okay, so that's why it's called a hazard. It's also related to this. People want to say that how long a machine can keep operating normally, right? Before having some problem, before running into some problem. So that's why it's called a hazard. It's an instantaneous probability of some problem happening at any point of time. Right? So that's also what we are interested in modeling, what we are interested in predicting, because that's also meaningful. Okay, it's actually later we can see that actually this will be directly linked to the duration. These two are linked. Mathematically they are linked. You can derive one from the other. All right. So for this reason, actually duration model, survival model sometimes is also called a hazard model. So those are all the same. Okay, you can hear all those are different names: duration model, survival model. All right, so let's look at the basic setup of this duration model. So what we have is, the time, right? So we want to, that's what we are interested in. So this one, the time, you can view that is the random variable. It's a dependent variable. All right, the duration itself, although, what we are saying is like in the, it's like a process, right? And then at a certain point of time, the state change happening. But you can model that. You can model that instead of model this entire process, you only model the value of the duration, the amount of the duration, the time period of the duration. So this t, you can view that is the dependent variable. All right, the duration is a dependent variable. So it's it's random. It can be longer, it can be shorter, right? So this time period. But then for each individual, we observe the realized value of this duration. Okay, so that's what we can model. So this becomes this dependent variable, the random variable. And then, we can model this duration is a random variable, right? And then it follows certain distribution. Then we can model that, okay, what is the distribution? Again, for distribution, usual distribution, we model that CDF and the PDF function. So we can specify, okay, what is the distribution of this duration for all those individuals? So the probability of this duration being less than or equal to a certain value, then that's specified by this f of t. Okay, and then correspondingly we have this PDF, the density of the duration. Okay, that is something we can specify. But again, this is just a general framework just to start. We haven't specified the actual form yet, right? But just basically that's what we can specify, the CDF for the duration and the PDF for the duration. Now, if we know the CDF of a duration, we can do 1 minus f of t. Then that gives us what? That gives us this is the probability of the duration being less than or equal to a particular value. 1 minus this is the probability of this duration being greater than that value. So then what does that mean?
Then how many years will you survive also?
Exactly, survive beyond that period of time. So that's why this 1 minus f of t is also called a survival function. Okay, you measure the probability of an individual survive beyond this certain threshold, a certain value. Okay, so that's very, very straightforward. Now here comes this hazard function, very important. So how do we really define the hazard function? It's defined this way. All right, this is the formula. The hazard function is lambda. We denote that as lambda. Lambda of t. You see, it's a function of t, meaning that the hazard function can change with t. As time goes by, at each different time instant, the hazard can be different. All right, it's a function of t. And then it's defined this way. What is a hazard? You see, probability of this duration, being greater than t, being less than t plus h. So the probability of this duration falls into this tiny interval from t to t plus h. Okay, given that this individual has already survived past t. Okay, so in other words, it's what? That means the probability for this time, the state change to happen exactly within this small time interval, t plus t to t plus h. Is that clear? Is this expression clear? Right, given that the individual has already survived until t, and then the duration, the length of the duration is only, between t and the t plus h. That means the state change must happen within this small time interval, t to t plus h. Okay, the probability of this state change happening within that small time interval from t to t plus h. And then we, and divided by the length of that small time interval h. And then we take a limit for this h to become infinitely small. So what is this? Is this type of definition familiar? Think about it. Where else do we see this type of definition? Sort of an instantaneous measure, right? Some probability within an infinitesimal interval. Where else did we see some measure like that? Derivative. It's exactly derivative. So where else do we see? All right. So when we define probability density function of the distribution of a random variable, actually that the PDF, the density function's definition is very similar to this. Recall that what is the probability density function definition? F of t. What does that mean? Small f of t. The probability of this focal random variable for its value to fall into this very small interval from t to t plus delta t, right? Instantaneous, the infinitesimal interval, and for this delta t to be infinitely close to 0. Take the limit. So that, infinitesimal small interval, the probability for this random variable's value to fall into that small interval, that probability is, even the limit of that probability is the definition of density. So that's why you are right, it's actually the derivative of the CDF, right, with respect to t. All right, so in this sense, this hazard function, the definition of a hazard is actually corresponding to the hazard. This is for this, if you view this whole thing, this duration model is actually modeling a stochastic process, a random process. Okay, it's not a static it's like not a static state. It's a process, right? It's over time from 0 all the way, to all those different time instants. And then the process, at any time instant in this entire process, this state change could happen. So the hazard function is actually just modeling the instantaneous probability of state change in this entire process. Okay, at any time instant in this entire process, what's the probability of state change happening at any point of time? So hazard for a random process is similar to the density function for the distribution of a random variable. All right, the role of hazard function for random processes is just like the role of density function for the distribution of a random variable. Just keep that in mind. It plays exactly the same role. All right, so when you study random process, the stochastic process, we will start with this hazard function. We'll specify what is the hazard function. And then once you know the hazard function, you pretty much know the entire random process, because the whole process actually is governed by this hazard function. Hazard function, at any point of time during this entire process, right, what's the probability of state change. Then if you define that, you know how this process will play out eventually. All right, so just like if you know the PDF of the distribution of a random variable, then you know the entire distribution. It's the same idea. All right, so that's why hazard function is very important for stochastic process. So given this definition, we can write out that what's the probability for this t to be exactly between t and the t plus delta h, what's the probability? And write this way, right? This is like a density, so it's the lambda t times delta h. Of course, this delta h has to be infinitesimally small. It has to be very small. All right, so then this is this. Again, this is the idea like the density, like the derivative. All right, so that's the definition. Again, intuitively you can think of that as an instantaneous probability density of an individual exiting the current state at any time instant t. Of course, conditional on that he or she has already survived until that point of time. All right. So now we said that the hazard, just like the distribution, the density function for a distribution. Once you know hazard, once you know PDF, you can derive CDF. Right? Similarly, once we know lambda t, the hazard function, can we derive the distribution of this duration t? You see, hazard definition itself doesn't really have t there, right? So the distribution is each time instant. Each small time instant, what's the density, right? What's the probability density? So it doesn't directly have the entire duration there. But if we know the hazard function, can we derive the expected value of duration t? Do we know the distribution of the duration t? Yes, actually we can. Of course we can. So you can derive this. So the hazard, by the definition, we can write it this way, right? So that it's the probability of the duration to be between this small interval from t to t plus h. So what's the probability? You can write this way, right? As the CDF for the duration t, right? To be f of t plus h minus f of t and divided by h. This is just according to this definition, right? The numerator here is just the probability of this. And then you divide it by t. And of course, because it's has this condition, so it has to, be conditional on this, the survival. The individual has already survived past that t. So there you do that, you do some, this one, basically, this one gives you this, the density, right? So f of t. So, it's just equal to this. So essentially, the hazard function can be written as the density function of the duration t divided by this one, which is the survival function of t. All right, this is just from the definition, the relationship. The hazard function is equal to the density of the duration divided by the survival function. Okay, so make sure you understand those values. So this is the density of the duration of, again, duration t as a random variable, its distribution, the distribution of its value. And then divided by the survival function. The survival function is just defined as 1 minus f of t, which the f of t is the CDF. Again, CTF of the value of the distribution of this duration. So that's equal to this. This is by definition. So now, because of this this equivalence, this equation, we can write this one. You see, we utilize this relationship. S of t is equal to 1 minus of ft, right? So you can write this way. You see, log of st, we take a derivative. That's equal to what? If you take a derivative of log of st with respect to t, what do you get? You take a log, right? So the chain rule, take a log, and s, that's 1 over s of t, right? It goes to the denominator. And then you further take a derivative of st with respect to t. And then what do you get? Because st is equal to 1 minus ft, right? Then you take a derivative of st with respect to t. Then you basically get a negative. Then take a derivative of ft with respect to t. Then what do you get? You get this small f, right? The density f. So then you have a negative f over st, and then that's why we add a negative sign there. You see, based on this, then we have this duration, this hazard function can be written, can be derived as equal to this minus of derivative of log of st. All right, so this equation is very important. Basically, what does that do? Link the hazard function to the survival function. And the survival function is essentially just the PDF or the CDF function of this duration of t. Right? It's just 1 minus the CDF function. So survival function is essentially just f of t. The CDF of the distribution of the duration of t, duration value. So this equation, this relationship simply just link the hazard function to the distribution of duration t. Okay, so that's the relationship. And as a result, we can derive the survival function as this. Okay, again, log of survival function derivative is equal to lambda. So the survival function itself is, we first integrate, right, the duration out of the hazard lambda s over, t, and then, negative, and then put that into the exponential function. That's just the inverse calculation from this equation. You see, again, these two equations essentially are the same. Basically, just link survival function to the hazard function. And then, like we just said, the survival function is just 1 minus ft. So as a result, ft is simply equal to 1 minus this survival function. All right, you see, that's why I told you, once you know the hazard function, once you define the hazard function, you can derive the distribution of this duration t. And vice versa, once you know the distribution of duration t, you can derive the hazard function. Okay, mathematically they are equivalent. So that's why when we specify those, the random process, the stochastic process like that, you could do either way. You could start with the distribution of the duration. You specify that. Then you also know the whole process because you can derive the hazard function at any point of time. Or alternatively, you can specify the hazard function at any point of time. Then as a result, you also know the distribution of the duration values. Okay? Then if you further take, that's interesting. If you further take the derivative of this, right, f of t, then you know the PDF is small f t. Question?
Can you explain again from the first line to the second line why you take the log?
So if you take a look, this is just based on based on derived action, but you can, it's easier for you to understand from here to here. Yeah, you take a derivative of log of st, it will give you this, right? You take derivative of log of something, it's 1 over that value, right? Then you apply the chain rule, and then you further take. Got it? Take a chain rule, right? So you take a log of fx with respect to x. How do you do this derivative? First do the log, right? It's the derivative of log of something. So you first do that. So it's f of x, 1 over that. That's the derivative of log. Okay, and then you take chain rule, further take the derivative of f with respect to x. So this is this. So this actually, it's a good that you asked that. Everybody make sure you understand how this is done because this is very commonly used, this relationship. We already saw this in last topic. Can you recall? Where did we see this? Last time for count data model. Remember, for Poisson regression model, what's the expected value of y?
Lambda.
That's the expected value of y, right? And then we said that, what did we do? What's the meaning, interpretation of beta? We can do what? Take the logarithm on both sides. And then take a derivative, right? We take the derivative with respect to x, a particular x, on both sides. What do we get? It's beta j. And here is what? This is exactly this. 1 over e of y. Right? And then take the derivative of e of y over x. So then that's what we said. In Poisson regression, what's the meaning of a beta coefficient? Forgot about that? Meaning the percentage, the partial effect, but it's the percentage effect, right? When x increases by 1 unit, what's the percentage change it will induce on expected value of y? Remember? This one, the delta of ey, the change in expected value of y, divided by expected value of y itself. So that's the percentage change, right, in expected value of y. You see, that's exactly this. We take the logarithm of ey with respect to x, which is equal to 1 over that value first, and then you take that derivative. The same calculation. All right, so that's why logarithm. If you take a logarithm, basically that reflects the percentage change. Exactly because of that. Because if you take a derivative with respect to log of something, that's what you get. So then, because you have 1 over this function value itself, so that's why what you get here is the percentage change. So that's why you see some people will specify the model as a log of y is equal to something. So that means if you specify the model like that, then the beta coefficient is simply measure the effect of x on the percentage change of y. Just because of that. All right, so yeah, make sure you are familiar with this derivative. This is what we're going to use often. Actually, for today's topic, for this duration survival model, later on for the interpretation of beta coefficient, we're going to see this again. All right, if you have a log of something, you take a derivative, then you get the percentage change. All right. Okay, now understanding this relationship, now think about that. We can specify either one, right? We can specify starting from the Hazard function or starting from the distribution of the duration. Either way, it will define the random process, this whole survival process for us. So now think about that. How can we specify Hazard function? Later on we're gonna talk about all those. We haven't really specified any model yet, right? So this is just a basic setup, the framework. So now, if we want to specify a model, specify this process, this survival, this duration process. What can we specify? We can specify, this Hazard function, right? How Hazard? But remember, Hazard function is a function of time, of t. So basically, it's the Hazard, the instantaneous probability density. How does that change with time? At any point of time, how does it change? Okay, so we can specify that as a very complex function of t, right? And that means the Hazard rate changes with t. Okay, and follow you can make it very complex. But what's the simplest possible way of specifying Hazard function? Constant, exactly. Just the Hazard function is a constant. It doesn't really depend on time. It's always equal to a certain value, certain constant. Actually, this is actually not trivial. This is actually a very commonly used model. It's a very common random process. This process is called what? Poisson process. All right, the Poisson process is at any point of time, the Hazard rate is the same. It's equal to a certain value. So at any point of time, the probability of this the state change happening is always the same. If that's the case, think about that. What is the key feature of this process, a process like that? Does that depend on history? Does that depend on how much time has already passed? No, right? Because it's a constant, so it doesn't depend on history. No matter whether we are talking about a t at 0, t at 1 hour, t at 1 day, it doesn't matter because any point of time, it's always lambda, always this constant. So it doesn't depend on history. So for this type of model, actually it's so-called memoryless. So it doesn't depend on how much time has passed. Okay, so this is, then follow this distribution. If this is the case, you can do some simple exercise. Then how can you derive the distribution of the duration t? Right? If the lambda, the hazard is always constant, then you plug in this. Then it's simple. It's much simpler because it's not a function of t. Then this integral is simply just lambda itself times the entire duration t. So then you can derive that. And then we can show that, easily show that if the hazard function is constant, then the duration t as a random variable itself follows what? Exponential distribution. Because you know f of t is equal to this. The PDF function small f of t is equal to this. This is the PDF for the so-called exponential distribution. So that's why for this Poisson process, its duration actually follows exponential distribution. So once you know that, you do not need to start with this. You can directly say, okay, for Poisson distribution, we just directly model the duration of t following this exponential distribution. Then what we are getting is a Poisson process. All right, so that's just the standard way, like the simplest way that we can model hazard function. But of course, we want to model that in a more, kind of general way, right? Not only just always a constant. Now, well, for a model, when you want to, you have a data, right? You want to develop a model to capture the data. You want to know that what factors would affect the duration. Right, that's usually what we know. We collect all the data, and the y variable is the duration, right? So for each individual observation, how long it has survived, and when this state change happens. But then you also observe a lot of other variables, other factors. Then we want to know that what factors would affect the expected duration. So as usual, you want to model the hazard function, but you also want to incorporate the so-called covariance, right? Incorporate all the x variables. So now, how can we do that? Well, we need some function, right? We need some functional form, some form for us to easily, model this the hazard function. And then we also want for us to be able to incorporate the covariance. Of course, in theory, you can model this hazard function, in any functional form, right? You can just come up with whatever functional form you are interested in and specify that as a hazard function. But also keep in mind, you want that function to be sort of easy to handle because you want to derive this, the distribution of the duration from hazard function, things like that. So you want the functional form to be able to be, to be integrated out, right? To have, closed form solution after this integral. Things like that. So that's why over the time people have developed those different families of models that can be used to model those hazard function, model those durations, and it's easy to handle. And it can also be flexible enough to fit the data well. Right? So that's why we have some model that we often use. So the most commonly used modeling framework is this called a proportional hazard model. Proportional hazard model works this way. We model the hazard function as the product of two parts. The first part itself, the core, is a hazard function, but it doesn't involve any x variables. Okay, it's just a function of t. This is called a baseline hazard. This is a function of your choice. Usually it's a flexible function, flexible baseline hazard function can fit the data well. Depending on the data, it has like a flexible parameters. So as the parameters taking different value, this hazard function takes different value and a different shape. The curve, takes different shape so that it can fit all kinds of data well. Alright, so it's like a flexible family of distribution. But it doesn't have any x variable. It's just a function of time. Okay? But then we multiply that baseline hazard by another coefficient. That coefficient itself is a function of all x variables. All right, and then we use this product as the function, the full function for the hazard of the process that we are modeling. So this type of model is called a proportional hazard. The meaning of the name is clear by itself, right? So it's proportional hazard. So we have a baseline hazard that's the same for all observations. And then we have this coefficient multiplied to that baseline hazard. So that coefficient will be different for each observation because that coefficient itself is a function of x variables, and each observation will have different x variables. So then that coefficient will be different. So that's why the hazard function across those different individual observations, they are actually proportional to each other. Is that clear? Is the setting clear? So, any question? So proportional hazard, okay? So for each individual observation, the baseline hazard is always the same. Okay, it's a function, it's a common function of time. It doesn't involve any x variables. Right, again, think about what data we are having, for this type of survival problem. The usual data, right? But now just the y value is what? You think about now the y value is what? Now it's the duration. For each individual record, what's the duration of survival? Okay, the time period of survival. And then the x variables are the usual x variables. Those usual factors, usual the attributes that you observe for each individual. All right, so but we want to see that how these effects affect the duration, affect the expected duration. And then we can come up with the proportional hazard model like that. So it's the product of two things. So the baseline hazard doesn't involve any x variables. So as a result, the baseline hazard is the same for each individual record, individual observation. Because it doesn't involve any x variables. So then it's the same. It's just a function of time. Then it's a common function of time. Same for everybody. But then how do we incorporate the difference? Right? Because everybody has a different duration. Then how do we incorporate that? We incorporate that through this coefficient in the front. All right, so each individual record, each individual observation has a different set of x variable values. So then that different x variable values will affect the coefficient, will lead to a different coefficient then, multiplied to that common baseline hazard. So as a result, for each individual, their hazard function is always proportional to each other. All right? So for this function, usually, we can make the most general form of this function is that this coefficient can also be dependent on t, can also change with t. But for the simple version, we will let it not depend on t. Otherwise, this coefficient only depends on all the x variables that you have. So it's constant throughout the t. So then as a result, the dependence on time is only captured by this common baseline hazard function. All right, so then the individual difference, individual heterogeneity is captured through this constant. But this constant, this coefficient is a constant for each individual. It's a constant over time, just multiplied to this baseline hazard function. That's the basic form of proportional hazard model. All right, of course, it's not the most general form because the dependence on time and dependence on all the x variables, they are modeled separately. So in this sense, we are imposing some restrictions on the structure. But it's flexible enough, for most common situations, it can incorporate, all those variants, it can incorporate individual heterogeneity, and it can also model all kinds of flexible time dependence. So that's why, and it's easy to deal with. So that's why this proportional hazard model is very commonly used for survival problems.
Can we also model this where the hazard is not constant?
No, this is model, the hazard is not constant. Now this one is no longer proportional hazard model, it's no longer constant hazard model. A constant hazard model is the simplest model. We seldom really do them in practice because it's too limited. It's only interesting, meaningful theoretically. Okay? But this one is not a constant hazard model because it's a function of t. You see, the hazard function is modeled as a function of t. But of course, the time dependence is captured only through this baseline hazard function. All right? Now, but for the hazard problem, what's the nature of what's the requirement for hazard? It has to be non-negative. Right? By definition, it's a density, it has to be non-negative. So for this reason, our model also need to be autonomously satisfy this requirement. So this entire hazard, the product of these two terms have to be non-negative for any time, for any x variable values. So for this reason, this we can take off that we specify functional form for this one. But how about this one? X values can take all those different values for each different observation. So how do we make sure that they are always non-negative? We already dealt with that last time, right? How do we make sure that we incorporate a flexible functional relationship with all x variables, but we want to make sure that the outcome is always non-negative? Then what do we do?
Exponent.
Exactly, put that into exponential. So we still do the usual x beta combination, right? So for each x variable, we give it a free parameter, free coefficient beta in the front. We do the linear combination, right? Beta 0 plus beta 1 times x1 plus beta 2 times x2, right? Like that. But then this linear combination, so all the beta parameters are free to estimate, so it can take any value. So the linear combination naturally will take positive, negative values. Then how do we ensure that the overall outcome is always non-negative? We insert that into this exponential function. Take the exponential of this x beta combination. And although this x beta combination can be positive or negative, but this exponential of x beta is always positive. All right, so then we simply use this as the k function, as the coefficient for proportional hazard. Okay, so that's how we model that and how we ensure that that's non-negative, that's always non-negative. All right, so for this part, we usually model this way. And for the baseline hazard, we can have different choices. All those, hazard function that have been studied, has been proposed, that has been well studied, well understood, we can consider choosing them. Okay, there are different families of baseline hazard function for us to choose from. Okay, so we're going to talk about next. Okay, but before that, given that once suppose we have chosen a baseline hazard function, and then we have specified the coefficient as this e to the x beta, so now we actually have the model. Okay, once we choose a baseline hazard function and we model this up, the coefficient involving x covariance as e of x beta, then we essentially specify the full model. All right, so then the full model for each observation, its hazard function is simply defined by this one. Right, the coefficient is e to the x of beta and times a certain baseline hazard function of our choice. Then the model is specified. Right, then for each observation, once we know its x variable values, we just plug in the x variable values. Then we know the coefficient. And then, given the baseline hazard function, then we know how the hazard rate for that observation changes over time. At any given time point, we know that what is the hazard rate for this particular individual. And then because of those relationship, we also know that what's the expected duration for each individual. Is that clear? So then the expected duration will be dependent on all the x variables. Okay, so that's the model, that's the proportional hazard. That's how we specify that, and then we can apply to our data. Okay, so then how to estimate this model? Then what are the coefficients to be estimated in a proportional hazard model? As usual, all the betas, right? So those are all free coefficients to estimate. Basically, how this duration changes, right, with all those x variables. And what else? There are usually parameters, free parameters inside this baseline hazard function, right, to model the dependence on time. So there are different parameters. So the parameters, just like the parameters in those distributional functions, it will determine the distribution, right, the shape of the distribution. And usually those distribution family, those survive the baseline hazard function family, they are very flexible. So then, depending on those values of those parameters, you can model any time dependence, any different forms of time dependence. So then, those distributional parameters inside this baseline hazard function are also parameters to be estimated, in this proportional hazard. All right, so usually for proportional hazard model, the coefficient, the parameters to estimate are all the usual beta coefficients and also those parameters inside the baseline hazard function. Then once we have that, how do we estimate that? Again, usually using the usual MLE estimation. All right, so MLE estimation, we need to write out the likelihood function. So now what is the likelihood function of observing the data observations in our data set? Again, for survival problem, what are our data? As usual, for each observation, you have all the X variables. But now what is the Y variable? Duration, exactly, the duration time, the time. You know, when, how long this individual has survived in the initial state. All right, so that's the time period, so the value of that duration. But now pay attention here. You know, for any observation, for any data set, we only have a limited observation period. Right, for any data set, you won't observe to the infinite future, right? So you have to, there will be a starting time point and an ending time point. So there's, you know, limited time. So then that means for some observations, it's likely that they have survived past that end of your observation window. It's possible. So for those observations, so we do not really observe when exactly this observation eventually exits the current state. Right? Basically, this observation, some observations simply survived until the end of your observation window. So for those cases, we will call those observations censored. All right, actually they are so-called right censored because they are censored on the right end of this observation window. So what we know is that their survival, the entire survival period is greater than, you know, what you have observed. That's all we know. We do not observe the eventual, you know, point of exit. All right. So, but for some observations, we know we observe their point of exit before the end of the observation window. So then we observe their precise duration period of time. But then those observations are called uncensored. But if they are censored, we do not really observe the exact duration of time. All we know is that their duration period is greater than what we have observed. All right, so this is important because when we write out the likelihood function, you need to treat these two groups of observations differently. Because one group you observe the exact value of this duration t. Another group you only observe the censored value of duration t. You only know that the duration for those observations is greater than, you know, the period that you have observed, but you don't know the exact value of this. So for those groups, it is very similar to our Tobin model, to our sensor data model. Okay, so for those values that it's censored. So that's why when we write out those likelihood function, we treat them differently. For those who have you observe the exact duration period, what's the likelihood function? Just the PDF. Okay, so you know the exact value of this t, this random variable t, duration t. So then this value, then what's the PDF, the density function for the value of that duration t as you observe? So that is the likelihood for that observation. Alright? But for the censored one, right? If it's censored, if you don't observe, then what's the likelihood? The likelihood is that the value of this duration for those observations are greater than what you have observed. So that's why you use this 1 minus big F of t. This is the survival function. Is that clear? So here the notation here, D is just the indicator, binary indicator. 1 means uncensored, 0 means censored. So if 1, you know, this term, the exponent is 1. This term, the exponent is 0. So this term goes away, right? So then for those uncensored observations, you simply use this one. And for those censored observations, the index is 0. So then this term, the exponent is 0. So this term goes away. And then this term, the exponent is 1. So essentially, only this one is effective. So you just use this form as the PDF for those censored observations. All right, this is just you know, an easy way to combine all those two scenarios into one equation. Nothing really complex. All right, essentially what I'm just talking about is just likelihood function. We treat them differently. The two types of observations, we treat them differently. For censored observations, we use the survival function, the CDF function, as the likelihood. And for the uncensored observation, we use the PDF density function as the likelihood. Okay, and then for each observation, you observe all the x values, right? And then whether it's survival or not, and you observe the duration, right? Whether being censored or not. So you observe those values, and then you just plug into that the either form of this likelihood function, and then you multiply the likelihood of all observations together. That gives you the entire likelihood function. And then we apply the usual maximum likelihood estimation to search for the parameter values that will maximize this entire likelihood. But again, because we have all those things, oftentimes we do the log likelihood, but essentially they are the same. You just take the logarithm. Instead of maximizing the original likelihood function, you maximize the log of that likelihood function. But that's the same because log function is increasing. So you might maximize log of a certain function is equivalent to maximizing that original function. But the good thing with log is that all the products becomes addition, becomes sum. So computationally it's a little bit easier to handle. But that's not really, nothing really big deal. I mean, you could start to do with the original likelihood, but usually we do that. All right. So the same way as how we estimated the Tobin model. Okay, same way as how we estimated all those, binary response model, content model. But it's because of the censorship, it's most similar to this Tobin model, how we estimated two groups of observations: the censored group and the uncensored group. All right, so that's the basic framework. Now, what's left unspecified is this one, right? We know how to specify this, in the proportional Hadron model. But what's still we haven't talked about is how we exactly can specify this baseline Hadron. So let's just talk about that. So we have a lot of different families, of baseline Hadron function that we can use. But the most one commonly used family is this so-called Weibull model. So we'll just talk about this model. Okay, just model the baseline Hadron function using the Weibull distribution. So this is the Weibull distribution. Okay, so Weibull distribution is a distribution. All right, so it's a distribution. So you can think of it as a distribution for this duration t. Okay, so then the distribution can be is defined like that. So, but the confusing part is that there are different forms of Weibull distribution. These are the three commonly seen forms, seen all those different books. So yeah, initially I was also a little bit confused because every time you see the description of a Weibull distribution, they may be different. But essentially they are the same. You can derive equivalence. Essentially these are three forms. They are essentially the structure is exactly the same. So it's about the same distribution, but just how they represent that, right? So the parameter they use, how they are, the parameter they use, the form is a little bit different. You see, some people use this A and B, this way. Some people introduce this lambda and A and alpha, this way. And yes, some book will use this one, right? You see, but you can derive equivalence. So in this way, this A over B is the gamma times alpha, right? Saying that you can derive equivalence. So they are essentially equivalent, but just pay attention that a different book may use different form of the distribution, and then the different parameters have different. Doesn't mean exactly the same, right? So you need to do some transformation from one form to another form. Right. So what just for simplicity, for consistency, we're gonna focus on this one, on this particular one. We'll just use this format. All right, we'll just use this format. This one. All right, we'll use this. So this is the PDF function of t, of the duration t. All right, PDF function. Again, duration is a random variable, right? And the PDF function of that duration t is this one. And this is the Weibull distribution. It has two parameters, A and B. Okay, three parameters. And with different parameter values, the function looks different. Can model different shapes. Okay, just like other distribution family, very flexible distribution family. And then given this PDF, we can derive the according CDF, right? As the integral of that. And also we talk about the equivalence, the linkage between the CDF function and the Haza function. So based on this CDF function, you can derive the Haza function. All right. So remember this. This is the Haza function of Weibull distribution. All right. This is the PDF, the CDF function of the duration. Duration is a random variable, right? So duration is the time. So it can take this time, 1.2 hours, right? 3.5 hours. So it's a value. The realization of that duration is a value. So it's just a random variable. This is the usual distribution. All right, this is the usual CDF function characterizing the distribution of this random variable t. But what is this? This is the Haza function. So this t, pay attention here, this t is no longer the realization of that duration t. Instead, this is like the time instant. But t measure is the same. Okay, so if this is 2.3 hour, the total duration, then this 2.3 here is also means that the time instant, right, as 2.3 hours after the initial starting point. But the meaning is different. This lambda t simply means measures the hazard rate at that t time instant. All right, so make sure you understand the difference. This f of t measures that the probability for the duration to be less than or equal to a certain value. For that, the probability for this individual to survive that long. All right, but this lambda of t, this density, this hazard function, it specifies the hazard rate at that time instant t, at that time point, the hazard rate. As we said, we have this equivalence. So this equivalence, so you can derive that from one to the other. Question?
So in all these models, f of t, little f of t is the PDF.
Yes, the PDF. The big F of t is the CDF.
Okay.
And S of t is the survival, which is 1 minus big F of t. And then lambda t is the Haza function.
Okay.
All right, so for survival model, these are the important values, important functions, and they are all linked to each other. So once you define one, you can derive all the others.
Is CDF always the integral?
Yes. All right, so these four, lambda, S, F, the big F, small f, they are all linked together. So once you define any of them, you can derive the rest.
When we were talking about the hazard function of the Weibull method, we talked about how the hazard function is kind of like the density function of a random variable.
Yes,
right?
yes.
So that's like the density function is the PDF, right? So then in this model, why is the PDF, or is the hazard function not the PDF, but the CDF?
Yeah. So hazard function is for this process, this entire process. At any time instant, what's the instantaneous probability density for the state changing event to occur? All right. So what I said is that the hazard function for this random process is similar to the role of PDF function for a distribution of a random variable. Okay, so that's the equivalent that I meant. But here, that's different. Here, when we talk about this PDF, this one, it's different. This is the PDF for that duration, that big T. You see? But this hazard function is the hazard function for that process, for this process that we are characterizing. So that's why these two are not the same thing. You see, this is the PDF for that duration, which is a different random, it's a random variable duration, right? So it's how long that individual has survived. So it has a value, right? So like I said, 1.2 hours. So then the 1.2, that's the value for that for the realization of that duration, that capital T, this random variable. So this PDF is describing the distribution of the value, possible values of that random variable. Okay, but this is the density function. This is this is the hazard function. That is the instantaneous hazard for that process. During any point of time in that process, what is the probability of that, like a state changing event happen, of like that so-called death happen? All right, so these two, that's why I said they are linked, but this and this, they are not modeling exactly the same thing. So that's why, although they are all using t as this, denoted as the t, but this t has different meaning. That clear? So this t here, for this PDF function, that's the value of that random variable, this duration. But this t is the time instant. All right, so make sure. Yeah, this is the fundamental structure of this the survival problem. Right? So always think about that. You have this timeline, right? So this is a starting point of our observation. So that at a certain point of time, for certain observation, right, for a certain individual in your data, at a certain point of time, right, the state change event happens. So that individual, quote unquote, dies. All right? That individual has survived from 0 to here. Then this big T, that's the duration of the how long this individual has survived. So then it's a random variable, right? Depending on when that individual dies, its value realizes. All right? So then in this sense, this individual, this duration from here to here, this T, now for this individual, when he dies here, it takes this value. That's its realized value. Okay? And then this is what this PDF and the CDF and the PDF is modeling. It's modeling the distribution of the possible values of this random variable, this duration. But then what is hazard function modeling? At any point of time, what's the instantaneous probability of death happening? All right? So then, at this point of time, we can also model this one. But the meaning is that at that point of time, conditional on that this individual has survived until then, what's the probability, instantaneous probability of death happening at that point of time? Of course, for the hazard function, at any point of time before that, we have a hazard function. All right, so that's the meaning of this T for hazard function. It's any given time instant along the process. What's the probability of instantaneous death?
In general, is the hazard function always the negative derivative of the survival model?
Yes. These relationships always hold in general. All right, so make sure you understand what they are modeling. What is lambda t exactly modeling? What is small f of t and big f of t modeling? All right, initially it could be a little bit confusing, because the meaning is slightly different, but they are linked because of their structure, right? Because if you know the instantaneous probability at any point of time, you will be able to derive what's the expected duration. How long can this individual, be expected to live? Right, so that's why inherently they are linked. But these two functions, lambda t versus f of t, these two functions per se, they are measuring different things.
It's always the derivative of natural log of S and t, not just S and t.
Yeah, these four equations always hold. All right, so let me just quickly show you the duration. All right, let me finish this slide. So this is the Weibull. This is the Weibull distribution. You see the Weibull distribution has two parameters, A and B. All right, again, these are, this is the Weibull distribution. This is the CDF, the PDF of this Weibull distribution. This is CDF. And then we can derive, using that formulas we just showed, we can derive the hazard function for Weibull distribution as this. Now, this is important. You see, this Weibull distribution, make sure you are familiar with this one. You see, take a look at what's the structure of this Weibull distribution. These are all coefficients, A and B, right? So they are coefficients, they are like a constant. So the real time dependence is what? T here, okay? T over, this exponent A minus 1. Alright, then we have two parameters, A and B. A is called the shape parameter, and B is called the scale parameter. Why? Because A appears in the exponent, so it determines the shape. B is only appear as a coefficient. It's like the coefficient multiplied in the front, so it determines the scale. Alright? So you see, different A and B, it can model different shape. Now think about it. What if A is equal to 1? If A is equal to 1, this exponent is gone. Then as a result, what do we have? Exactly, constant hazard. Then hazard becomes constant. Okay, hazard becomes constant, then what do we get? The Poisson process, remember this. But what if A is greater than 1? Exponent is positive. Positive exponent, what does that mean? Exactly, increasing in t. Increasing t means what? As t goes by, as time goes by, the hazard rate increases. All right, so that means if the patient keeps surviving, the longer the patient survives, the more likely, the riskier, he or she is in, the more likely that he or she will die at any point of time. Okay, but if A is less than 1, it's negative. Then what do we have? As time goes by, the hazard rate decreases. So the longer a patient has survived, the safer he or she will be. All right, so that's why the Weibull function is very flexible. It can model all those different types of time dependency depending on what you have. All right, so we're going to stop here. We're going to talk about that time. Continue to talk about that. All right, see you next week.